welcome back. Wish you all good health, strength, peace and enjoy with your family in this time of pandemic. And today is the birthday of Swami Vivekananda. So, pray to Swamiji. May God bless all of you. May all be happy and may all be free from disease and difficulties. Today, I will discuss all ring homomorphism theorem. We all of us know, in my earlier video, I had seen the first ring homomorphism theorem and I had discussed more exercise about the first ring homomorphism theorem. We all of us know. First, I will recommend you, if you don't see my previous video, please see my earlier video. Second isomorphism theorem is, we all of us know about the sum s plus I, which is equal to set of those elements small s plus I, where small s belongs to capital S and small I belongs to capital I. And this sum obviously we all of us know this is a subring of R, which I had discussed in my previous video. Then their intersection means S intersection I will be ideal of S. And the following quotient ring here, isomorphic to S plus I modulo I, which is isomorphic to S modulo S intersection I. And this is the picture. Here the whole ring R, which contain S plus I, and S plus I contain both S and I, and both contain in S intersection I. Then this is the subring and here I be ideal. Then by second isomorphism theorem, we can tell S plus I modulo I is isomorphic to S modulo S intersection I. This is the same like second isomorphism theorem of a group theory. In group theory, just recall G be a group and S and N be two subgroup of the group G, and assume N is a normal subgroup. Then their intersection S intersection N will be normal subgroup of S, we all of us know. And second, their product Sn is subgroup, and where N be normal subgroup of this product Sn. Then by second isomorphism theorem, we can tell by first, since S intersection N is a normal subgroup of S, so we can tell S modulo S intersection N is isomorphic to. Second, notice in the subgroup Sn, N is a normal subgroup of Sn, so this is isomorphic to Sn modulo N. And this is the picture, same like second ring isomorphism theorem. Okay, are you getting? Well, for example, consider G equal to S4 and N equal to Kiln4 group. We all of us know this is the Kiln4 group. We all of us know in S4, Kiln4 group is normal subgroup and S is those subgroup which is generated by 1, 2, 3 and 1, 2. And this is actually nothing but S3. In order of Sn, by the definition, this is equal to order of S times order of N divided by S intersection N. That means this is equal to 6 times 4, and here S intersection N equal to just singleton set 1. Put this value, then this would be 1. That means this value Sn order of Asn equal to 24. And we all of us know the only subgroup of S4 of order 24 is itself. Then by second isomorphism theorem we can tell S4 modulo V4 is which is equal to Asn modulo N, which would be by second isomorphism theorem isomorphic to A's modulo A's intersection N, and just put the value. This would be S3 modulo singleton set 1. That means by second isomorphism theorem S4 modulo V4, that means Killen4 group, is isomorphic to S3. Are you getting? Well, first I will say the third isomorphism theorem in group theory. Let capital G be a group and let A's and N be two normal subgroup of G such that N contain A's and A's contain G. Then A's modulo N is a normal subgroup of G modulo N. And second, G modulo A's is isomorphic to G modulo N quotient A's modulo N. Okay, this is the third isomorphism theorem for group theory. The third ring isomorphism theorem is similar to group isomorphism theorem. Here ideal. Let I and J be two ideal of the ring R with the condition here I contain J. Then J mod I is an ideal of R mod I. Then by third isomorphism theorem R mod I mod Z mod I is isomorphic to R mod J. I will see this proof. Here I will prove this theorem by first isomorphism theorem. Consider a mapping F from R mod I to R mod J, and the defined mapping is F of R plus I equal to R plus J, where all small r belongs to the ring R. At first we have to prove group homomorphism, and consider two arbitrary element R1 plus I and R2 plus I belongs to. Here the ring is R mod I. Notice. Then f of R1 plus I plus R2 plus I, which is equal to f of R1 plus R2 plus I, and by the defined function this value equal to R1 plus R2 plus J, and by the property of quotient ring we can write it as R1 plus J plus R2 plus J, and R1 plus J equal to actually f of R1 plus I and R2 plus J equal to f of R2 plus I. Their multiplication would be f of R1 plus I times R2 plus I. By the property of quotient ring we can write it as f of R1 R2 plus I, which is actually by defined function R1 R2 plus J, and also by property of quotient ring we can write it as R1 plus J times R2 plus J, and R1 plus J equal to f of R1 plus I and R2 plus J equal to f of R2 plus I. That means this value is equal to f of R1 plus I times f of R2 plus I. That means obviously this mapping is ring homomorphism. Now we have to check the mapping is onto. Since the mapping is defined f from R modulo R to R modulo J, consider a arbitrary element R plus J belongs to R modulo J. Consider this is an arbitrary element. Then Obviously, there exists R plus I in the domain R modulo I such that f of R plus I equal to R plus J. That means obviously this mapping is onto mapping. Then by first isomorphism theorem, we can tell R mod I modulo car f is isomorphic to R mod J. Now we have to find the kernel of f. Kernel of f equal to such R plus I belongs to capital R modulo I such that f of small r plus I equal to capital J. And f of small r plus I means R plus J equal to J. That implies from this line we can tell R belongs to the ideal capital J. J is an ideal of the ring R, and notice the element J modulo R is look like R plus I such that R belongs to J. It is the element of the kernel of A. This is the set of those elements R plus capital I belongs to R modulo I such that R belongs to the ideal, small r belongs to the ideal J. That means this is actually equal to J modulo I, because J modulo I is look like this type. So kernel of f equal to J modulo I. Therefore, we can tell R modulo I modulo Z modulo I is isomorphic to R modulo J. This is our proof. Okay? That means our proof has done. Okay? For example, consider G equal to integer and K equal to 6Z and A is equal to 2Z. And obviously K contain in A's, and if I contain G mod K, then this has 6 elements: 6Z, 1 plus 6Z, 2 plus 6Z, 3 plus 6Z, 4 plus 6Z, 5 plus 6Z, quotient ring 2Z mod 6Z. Out of this only contain 3 elements. This is 6Z, 2 plus 6Z and 4 plus 6Z. That means this is 6Z, 2 plus 6Z and 4 plus 6Z. These elements are contained in this quotient ring. Therefore, by third isomorphism theorem, we can tell Z mod 6Z modulo 2Z mod 6Z is isomorphic to Z2, because Z mod 6Z contains 6 quotient and 2Z mod 6Z contain 3 quotient. So, obviously this would be isomorphic to Z2, or this is isomorphic to Z6 modulo cyclic subgroup generated by 2 or Z modulo 2Z. Are you getting the third isomorphism theorem? I will see the fourth isomorphism for rings. This is, let I be an ideal of the ring R, then there exists a corresponds A to A mod I, which is an inclusion bisective between the set of subring A of the ring R that contains I and the set of subring R mod I. Furthermore, in case ideal A, which is a subring contains the ideal I, is an ideal of the ring R if A mod I is an ideal of R mod I. Okay. As for example, consider r equal to integer and I equal to 12z. So r mod I is isomorphic to z mod 12z. Then the subring of or ideal of 12z contains I, z, 2z, 3z, 4z, 6z and 12z. We all of us know this is. Then subring or ideal of z mod 12z would be z mod 12z, 2z mod 12z, 3z mod 12z, 4z mod 12z, 6z mod 12z and 12z mod 12z. This is the question. How many subgroups exist in the quotient ring z mod 12z? Then this answer would be this. Are you getting? OL. Today I will stop here. In my next video, I will discuss this topic elaborately. But at first, I will highly recommend you, please pay attention to today's video. See you soon, stay safe and stay positive always. And if you have any queries about my channel, then do comment in comment box. And don't forget to subscribe my channel to get more information about my channel.